Now voice should be coming through. Now voice should be coming through. Man, oh man, oh man. Now voice should be coming through. Oh, now there's echo. There's all kinds of stuff going on. Boy, what a unprofessional stream this is becoming tonight. So anyway, back to where I was. I've now got voice, got my blue snowball going. I had HD60S, my Elgato from earlier, chosen for sound levels. But this is where we're at, correlation and regression. I'm going to do a quick mini lesson so that you have this available to you. We talked about it last week. We'll talk about it again this week and finish it up this week. And then I think we have, excuse me, one more Wednesday night class. Then we have Thanksgiving. And then we have, I think, our final. So I'll have to go back and double check that. I'll remind you this Wednesday if that's what it is. But I think that's what it is. So let's finish up here with correlation, linear regression techniques. So as stated a second ago when my mic wasn't up, but correlation is a relationship. It's a relationship between two statistical variables. We're measuring them from the same population. We only consider linear correlation, or we will only be considering linear correlation. And there's really three types of it. Starting right here, there's a positive linear correlation, and I think I've already got my series set up, but everything else has gone awry, so maybe not. So if you look right down here, these points all seem to go in a pretty straight line. That's slope, in other words, your rise over the run. So the slope is positive. So that would be a positive linear correlation. Okay. That's on the example. So height versus weight for the adults. So the more weight you have on an adult, typically you have more height. It's not always the case, but typically when you're looking at your data, that's what you're going to have, which is what's represented in this graph right here. Now, blood alcohol versus reaction time, that's right here in this second graph, scatter plot of crash avoidance, reaction times versus blood alcohol content. Now, this has several lines, several best fits through there, several representations from a research study. Disregard those. All I'm looking at is the fact that these all seem to follow a positive linear. In other words, we could put a spaghetti noodle straight line through it, and those points line up on either side of it in a pretty good fashion. Okay. There's also a negative linear correlation. If you're looking at the age of a vehicle versus the retail value of a Ford F-150 truck, what's going to happen with that? Well, the age of the vehicle, the older it is, the lower the retail value typically, right? If it's just a regular old Ford F-150 truck and it's older, it's 10 years older, so it's not going to be worth as much as it was 10 years ago. That's going to be a negative linear correlation. Reaction time versus hours of sleep for the previous night, same thing. Your reaction time is going to go down. Time out. Let's think about this one. Reaction time versus hours of sleep. I'm thinking that's not a very good example that I put up here. No, I see what it's saying. So your reaction time is going to take longer given that you've had less hours of sleep. So if you've had less hours, like if you've got 0, 1 hour of sleep, 2 hours of sleep, 3, and so on, the less hours of sleep, the longer time it's going to take you to react. That is a good example. It's going to look something similar to that. And then you can draw a line right through there. And then right over here, same idea. And you're drawing a line, and we're going to define this line when we talk about regression lines. Not tonight, I'm just doing a general overview tonight. But when we talk about this in class, we're going to define these lines both computationally with mathematics. And we're also going to talk about what it does, what we minimize here when we get that line of best fit. Right now, we're just eyeballing it for the time being. We're just making sure that these points line up in a negative linear fashion, positive linear fashion, or maybe not a linear fashion, which is what we're going to look at right now. All right, if you have no linear correlation, these are not the only examples. I don't see them up here. There they are. These are not the only examples. I put these graphs in a bad spot, but you can see the one that's covered up by my head a little bit there is a smiley face, looks like a parabola. There's no linear correlation there. It doesn't mean that there's no correlation, but there's no linear correlation there. And there's no correlation at all, it doesn't look like, with the circle. In other words, specifically with the linear, because I can put a line here, I can put a line here, put a line there. It doesn't really seem to make a difference where I put that line. In the second one, where it looks like a parabolic shape, I think I could have a line of best fit. It's just not going to be a linear. And all we're working with right here is linear relations. And we're talking about linear correlations. We're working with correlation coefficients. We're not working with, say, a parabolic fit or anything like that. Not in this class. Okay. So we could have no linear correlation. So I've got height versus number of years of education. You're no taller, given that you have lots of years of education, than you would be if you had no years of education. You could be short, tall with none, short, tall with many. It doesn't matter. It's going to be it should be all over the place. Day of the year versus hours of daylight. So the day of the year, is there going to be, that's probably more like that second graph. So day of the year versus hours of daylight. So you're going to have more hours of daylight at certain times of year than you would others. It also, that would depend on location, right? If you're in Alaska, that might skew that data. So I don't know if that's the easiest one to talk about. But just for wherever you're at in the moment, the day of the year should not really affect the hours of daylight in a linear fashion. Forgetting where I'm at. I was about to hit down again on Doceri and send this flying. Okay, I finally got my graphs up a little bit. So basically what we're looking at, we've got a positive linear association. We can put a line of best fit through there that has a positive slope. We have negative linear association, which is right here. We can put a line of best fit right through there. There are many lines of best fit. There's one that is the best. There's one that is a better fit than the others. There's one that is considered the best fit. But we can put several linears in there. But all the dots line up there. In a nonlinear association, this looks like it might be an exponential, but it's not a linear. And this no association, it doesn't matter where you put that. You don't really see a difference with each one of those. That doesn't go in any kind of pattern in a positive direction or negative direction. Okay, and all we're doing, we're going to judge right now the strength of our correlation, strength of our linear correlation based on the graph that we've got. I'm going to look at these graphs right here. That's okay. So if I were to draw a line of best fit through here, that line of best fit almost fits perfectly through those points. So I'm going to define correlation coefficient in a second, but I'm going to say that it has a pretty strong relationship. That correlation coefficient for this particular sample, I'm going to say, is probably 0.91. Then I'm going to look at this second one here. This also looks like a very strong correlation, very strong relationship between the x and the y variables. And I'm going to go, since it's got a negative slope, I'm going to say r equals negative 0.91. That's just a glancing at the graph and looking at it. Now, I can do a linear correlation with this apparently nonlinear association, but it's going to look something like that, right? And I'm going to say that my correlation coefficient is not drastically horrible, but I'm going to say it's about 0.61. Again, I'm just making a rough estimate. I don't have any data necessarily for this particular picture that I've got up here. And then on this last one, there's no association. I can put a line of best fit through there. And it may go something like that. Like I could actually crunch those numbers and do a line of best fit. But your correlation, the association and relationship between that independent and dependent variable is not going to be good. So you're going to have R is going to be approximately, I'm going to say on this one, 47. I'm just looking at the graphs and kind of assuming what the correlation coefficient might be based on the graph. I'm a little out of sorts with my stream. I'm having to go here and here, back and forth. Okay. We've already talked about this. Now here's some other examples. These are right out of our Larson text, the one that I use. We've got a PDF of. Perfect positive correlation is one that is where the correlation coefficient equals 1. And let me go ahead and define that range of values for the correlation coefficient. So the correlation coefficient is for this samples is defined by R. Whoops. And it can fall between 1 and -1. That correlation coefficient, as it gets closer to 1, is a very strong positive linear. As it gets closer to -1 is a very strong negative linear. Anywhere in between, you're going to have to make the determination as a researcher how you feel the relationship is between those variables that you're working with. Remember, we've talked about in class, if you're working with humans, the most variable of all things to research, then maybe a 0.53 is okay. Maybe you're going to use that regardless. But if you're dealing with blood alcohol content and reaction times, maybe 5.3 is just not strong and you're not going to use that. You're going to grab some more data. So if I look, if I look right here, these line up. Every one of these points is going to fit on that line. Therefore, it's a perfect R equals 1. When you look at this next one, this is a very good positive correlation here too. And you put that line of best fit through there, it's going to go something like that. That's a very good one. And what this example has it as is 0.81. I'd say that's pretty strong. As you start looking at the data points and they start moving all over, then you start getting something like this next one where, yes, you can put a line of best fit through there mathematically. You certainly can. You put a trend line, or whatever you want to call it. But your correlation coefficient, the relationship between those points, is not going to be as good because you've got some spread outs, right? You've got some outliers in many different directions with that particular one. Now, when you go to the bottom down here, I didn't really draw that well, but all of those fit on the line. Therefore, it is a correlation coefficient of -1. And remember, it goes from -1 to 1 inclusive. It can be 1 or -1. In this case, that is a -1, which is strong. So the negative indicates direction. It's not like the normal curve in that respect, but if you remember when we were working with measures of position, that negative just indicates the direction away from the mean. It just means you're on this side as you're facing it of the normal curve. Doesn't mean it's a negative number necessarily. It's just less than the mean. In this case, it indicates direction in the sense of slope. All right, we're looking at this next one here. And again, I think this is a very good, I didn't draw a very good straight line. And you're looking at R equals -0.92. I would agree. And then in this last one, which, by the way, graphs can be elusive. When you look at them, they may give off the illusion of being no correlation. But when you look at them, when you squeeze it in or pull it out, it may have a correlation. So it's better to run the mathematics on it. In this case, just looking at this graph, it doesn't seem to have, I could put a line in there for sure, but it doesn't seem to have a strong correlation coefficient. So we're going to say it has no correlation there. All right. All right, graph the following using a scatter plot. X equals height, Y equals femur length. So you've got a femur in your body, that's a bone in your body, and your overall height. There is a relationship between the bone lengths and your height. In this case, we're looking at a femur. So let me switch to here. It's not very responsive tonight. I would assume I've got an older Mac and I'm running several programs, including Doceri, which is a bit of a hog. doesn't want to switch to my calculator, so let me try it this way, see if I can get it. Yay! There we go. I'm going to change the color of the calculator because I don't like where everything is same color. By the way, this example, part of it slid off the screen. I didn't mean to do that here, but I'll include all the numbers in the calculator itself. So let me. Do I want to go pink? That shows up very well. Green, orange. I'm going to go orange. I'll push it all the way over there. Push green all the way over. See what that looks like. Pink. Yikes. Blue. And the gray. Well, the gray might be the best one, but I'm going to go with orange tonight. Okay. Second exit. And let's go back. Let's go into our stat menu, which on this calculator that I bought on Apple says stats menu, but it's the stat menu. And then I'm going to go into edit. Going to go up to the top. I'm going to hit clear and enter to clear everything out. I'm going to put these numbers from the table here, the independent numbers in and the dependent numbers in, and they correspond. 70.8 has to line up with 42.5. They were collected in that manner. In other words, the age of the individual is 70.8. The weight in kilograms, whatever, is 42.5, whatever you're studying, or the reaction time. So you have to make sure they go in line. So you're looking for the relationship that you're studying. So I've got 70.8, 66.2, 71.7, 68.7, 67.6, 69.2, 66.5, 67.2, 68.3, and 65.6, okay? Let's hit enter. Enter. All right, 65.6, 68, 67, 66, 69, 67, 68, 71, 66, and 70.8. So I just double checked all those just to make sure I don't have any flaws. I've got 42.5, enter. 40.2, I'll check them each time. This time I don't have my glasses. 44.4, and the font's small on here. 42.8. Thought so. 42.8. I still don't think it took. 42.8. There it goes. 40. Now, in my original graph, I got 473, but it should be 47.3. 43.4. 40.1. 42.1. And 36. And there we go. So I've got it all in here. What I'm trying to do here, by the way, I'm putting these in the calculator because I'm going to graph it. So I'm going to show you how to graph these scatter plots in the calculator. If you look above y equals, so if you have a calculator handy, if you look above y equals, you'll see stat plot. It actually says stat plot on the regular calculator. On this knockoff version that I got from Apple, it says plot. But I'm going to go second plot. And it's already selected one, so I'm going to hit enter. And I'm going to scroll back to on. And I'm going to scroll down. It's already selected for a scatter plot. I'm good. It already has my input variable, my x values in L1, my output in L2, and I want it to be this right there. Do I want it to be red? Yeah, I guess we'll take it as red. So I hit graph. And of course, there's my graph and nothing shows up. I put all those numbers in and nothing shows up. But if you notice here, my graph is set at like 10, -10. Let's look at the window. like 10, negative 10, negative 10 to 10 on the x and y value. So I need to zoom in on whatever I've got in the stat function. So I go zoom, and I scroll down to zoom stat, hit enter, and there they are. Now, unfortunately, I don't think, in fact, I know I can't. I'd love to draw on here, but I can't. We've got to set it up. But anyway, you get the idea. So it looks like from left to right, we're going up. So it looks like if I put a spaghetti noodle line of best fit, straight line in there, that these points would line up on it. So I'm going to say that my correlation coefficient is probably R equals, it's not going to be like 91 or anything. I think it's going to be like R equals 82. That's what I'm going to run with. R equals 82. Now I'm going to do something else here. And those of you who watch this video are going to have some insight into where we're going with correlation coefficient. However, we're going to backtrack and certainly do it computationally. Second exit. It takes me a second sometimes on this online calculator because stuff is slightly askew. So I'm going to go second catalog. And it's different. So I'm going to go stat, calc, regression. It looks like this is a little bit different. It's already did it for. We've already done it for me. So 0.65. I forgot what I said, but it wasn't a real high one. I think I said the 60s. Maybe I didn't. But 0.65 is going to be our correlation coefficient. So between -1 and 1, it does have a positive linear correlation, the strength of which is not super high, but it's at 0.65. I have no context other than we've taken the height and the weight of about 10 different people, or 10 different skeletons, however we looked at it. And in this particular sample, the correlation coefficient is 0.65. Okay. So let me back out of here. Stream Deck having issues. Thank you, Stream Deck, tonight. Not the Stream Deck's fault. It's my system's fault. This Mac that I've got is fantastic, but when you get too many things running, it just struggles a little bit. All right, so our correlation coefficient for this particular one, as brought about by the calculator, is approximately 0.65. So the relationship here, and remember that your correlation coefficient falls between -1 and 1. Take it as you will. Okay. Yeah, that's what we got. That looks a little bit better. That's a better color scheme than I got. This is straight from a TI calculator. And then if you see over there to the left, length is spelled wrong, but I can't go back into my table and change it now. Apologies. All right. Example 2. We've got another example here. The following table gives the weight, the X value, the weight in 1,000 pounds and highway fuel efficiency in miles per gallon for a sample of 13 cars. So a Chevrolet Camaro is about 3,500 pounds with 3,500 pounds, right? 30 miles to the gallon. Dodge about 2.5, 32, and so on and so forth down the line. 37 down there. Hyundai Accent, 2.29 in thousands, so 2,000, right at 2,000 pounds, and 37 miles to the gallon. Okay, so find, what was my next slide? I think I pushed it forward. Never mind. If I put it in the calculator, which I did, if I graphed it out and made a scatter plot, which I have here, this appears to be a negative linear correlation. And I would venture to say that this is pretty strong. So I would say that this is probably 0.86, and that's just me guesstimating by looking at the graph. Those points are pretty closely related there. Certainly doesn't go in a straight line where it's 1. I might have it a little bit too high. I don't remember what it was exactly when I did it out computationally. So this is how you find the correlation coefficient. I wrote this on the board last week. Every bit of this, all of this jumble of mess, is stuff that you already know. The X values, the values that we put into L1 for the particular example that I just did, not the pounds of the vehicles, the miles per gallon, but the one previous for the femur length and the height. That's what I put into the calculator. And you know all these. This is the N is the number of ordered pairs. Number of ordered pairs that we have. So we have some X, Y, we have 0, 1, 1, 5, 2, 10, whatever we're looking at all the way down. How many numbered pairs do we have? Of course, that would be 1, that would be 2, that would be 3, all the way down. So that's what N represents. The X values are just what they are. So in the case of the example that not really an example, but the numbers that I put at the side here, if I'm looking at the summation of X, Y, then I'm looking at 0 times 1 plus 1 times 5 plus 2 times 10 plus ... In this case, I don't have a terminating event. And you're just going to add all those up. That's the summation of the product of X and Y. The summation of the X's is just adding all of these up, multiplied by the summation of the Y's. So that's what this is and this is. So you take the summation of the product of the XY's multiplied by your number of ordered pairs, and then you subtract off the product of the summation of the X values times the summation of the Y values. I know that sounds like a lot, and it's a lot of room for error, certainly, depending on how big your set is. But this is where it's coming from. This is what I had this in class the other night. This is what we derive. As you look down here, you're looking at the square root of the number of ordered pairs times the summation of the X value squared. So square the X value plus square the X value plus square the X value. Subtract the sum of all the X values squared, and then you do the same thing with the Y values. So that's it. And again, I can't reiterate this enough. The range of that correlation coefficient is between -1 and 1 always. Is that good? Okay. I have talked about this. So the correlation coefficient will always be a number between -1 and 1. Positive value indicating a positive linear correlation. Negative indicating a negative linear correlation. I've talked about that just about every slide. A coefficient of 1 indicates a perfect positive linear correlation. Think about that for a second. And then a -1 indicates perfect linear. In your years of experience, can you think of anything that might come out to be perfect? You probably can, but very few things you're doing research on is going to come out to be a perfect 1 or a -1. But it certainly would survive in the sample space. There's a probability there that it would happen. 0 would indicate no linear correlation. The closer it is to 1 or -1, the stronger the correlation, and the closer to 0, the weaker the correlation. And I've talked about every bit of that throughout here. All right. I'm not going to walk through this. I'm probably coming to an end of what I'm doing here. I had a couple of kerfluffles with my stream. It was slowing down here. My system's a little bogged up. Got a little turned around with where my head was and some of the graphs, but nothing major. But I did want to come on here and just do a quick down and dirty, kind of what we talked about the other night in class. And I was going to go into a little bit more detail. I'm starting to burn out tonight. It's about 8 o'clock. So I think I'll close this particular one out, and I'll try to have some more as the week goes on. So what I was going to do here was just show you, if you look on this table, these are our values, if I'm not mistaken. They look like our same values. Let me look. 42, 40, 44. Yeah, these are our femur lengths. So, see if I can write on here. This is going to be your height, and this is going to be your femur length. So this is the same data that I worked with before, and I came out with, gosh, what did I put on there? I think it was a 0.65. I think the correlation coefficient was 0.65 when I did it on the calculator. I'm going to do it again, just for my own self. And I'm not really talking about the calculator tonight. I was just doing that for giggles. I'm talking about the general form of correlation and linear regression lines. So yeah, it was 0.65, 0.651 if you want to take it out to 3, which I think I do. But look right here. This is the product of xy. So if you take 70.8, 42.5, there's the product. Here's the x squared products. Here's the y squared products. You can do this right in the table like we've done with several other concepts and stats up to this point. This is the table, or this could be considered the table in your calculator. In other words, here's L1, L2, L3, L4, and L5. And then you just need to find the sum of these, which if you remember, you just go second stats to list, scroll over to math, scroll down to sum, and you'll be given this, and you can just do the sum of L1, sum of L2, and so on and so forth. Then you have all the numbers for the correlation coefficient. If you already have this in an Excel spreadsheet or in your calculator, it's very easy to calculate. You can calculate it piece by piece if you wanted to. Excel will do a trend line for you. The line of best fit for the calculator is done for you, so it's probably unnecessary, but I think it's very important to understand where these numbers come from. All right, let me round this out here. Oh boy, what is this? And there we go. Yay. I feel vindicated that something went right in this stream tonight. There it is. That's what I got. So I got that using the calculator function. This was gained by me working individual pieces of this and putting them in a separate table. No big deal, and then writing it down below. So but you see there's a lot of room for error here. That's the one big thing, as always, that you have to be careful with when you're working with binomial probabilities. That's a big, long combination, and then the probability of success to the x value times the probability of failure to the n minus that, whatever you're working with variables. And so there's a lot of room for error there as well. Same idea here. All right, this is where I'll stop. But if you take a look here, you see more of the same. You probably, as a student of mathematics, have seen, other than the hat on the y, have probably seen that y equals mxb many times for the slope-intercept form when you're working with algebraic properties or graphs. In the case of this, we're working with the same idea. We're going to get this y-intercept and this slope by using these particular formulas right here. We're going to work with those in class tomorrow night. So I think this is where I'm going to turn off the stream. I appreciate anybody that sat through this for a few minutes. I'm leaving this up here for my class. I'll try to remember to put up on the Moodle the link to this, but you all know where this site is. You've been out to several of my streams already. And I've got several other links in there. I think I've got a whole, I think I had a whole Moodle section for this, for where it's at on YouTube. So I've streamed this to Twitch and YouTube tonight. Certainly 2 locations if you need it. We'll finish talking about this tomorrow night. I appreciate any of you that stuck around for this. And we'll see you in class tomorrow night. See if I can get this to finish out. All right, and thanks for coming by. Appreciate it.